This video is going to discuss F equals ma, Newton's second law, for most of the video. To begin with, a few concepts. Again, inertia is resistance to a change in the velocity of the object. Resistance to the change in velocity. And we can measure the inertia by using mass. Mass measures the inertia. If an object has more mass, kilograms, it's going to have more inertia. A car versus a basketball. A car will have more inertia. Force is a push or a pull on an object. It's measured in newtons. We'll be using standard metric units. In honor of Isaac Newton, the unit of force is the newton. And our acceleration measures the rate of change of the velocity. Each second tells us how much the velocity is changing, how many meters per second of change we have. So acceleration measures the rate of change of the velocity. Then F equal ma, Newton's second law. The force here equals mass times acceleration. And it is important, very important, that the number you use for the force is the net external force on the object. You ignore any internal forces to the object or the system. We'll talk about systems in the future. But just use the net external force, and the force has to act on the object for which you want to know the acceleration. So direction of the acceleration and the force are the same. Those are some of the working principles we have in analyzing problems using F equals ma. Keep these items in mind. So an example here, mowing the lawn. This person's going to be pushing on the handle here, and the friction of the ground on the wheels provides a backward resistance to that, but there's a net force. We won't worry about the details of doing this net force in this particular problem. That'll come later when we examine the individual forces and add them up as vectors. Now let's suppose we have 51 newtons to the right is the net external force. What rate does the lawnmower accelerate to the right? What is the acceleration if the mass of the lawnmower is 18 kilograms? Well, we can use F equal ma for this. We algebraically solve this for the acceleration. It would be the force divided by the mass. And we have the numbers, 51 newtons for the force, 18 kilograms for the mass. When we divide newtons by kilograms, we will produce meters per second squared. And we have 2.83 meters per second squared off to the right. Acceleration has a direction. Again, the direction of the acceleration comes from the direction of the net force. Another example here, we won't work out any numbers, but rocket sled, the effect of the rockets is to create a thrust that's off to the right, a push off to the right. There's going to be some friction, at least air resistance, back to the left. The rocket sled has a weight downward. The ground pushes up on the rocket sled. And we can combine these again in a free body diagram. So we put a dot here instead of a full sled. We just, in the early chapters, we're just going to condense objects down to a single point. We have friction back to the left. There are 4 jet engines here. Each of them creates a thrust off to the right. So those vectors would add up. The weight vector down and the normal force of contact of the sled slats with the ground. These two forces add to 0 in the vertical direction. So Newton's first law will tell us since the net force is 0 vertically, there's not going to be any change in the velocity vertically. This object just is going to move horizontally. In the horizontal direction, you have to add up vectorly these 4 forces. They're parallel, so they can add directly, and subtract the friction. It's anti-parallel to the thrust of the rockets, so you can subtract that number, whatever it might be. Different example here, going down a slope, a skier going down a slope, and perhaps we want to know what the acceleration is going down this slope. If 25 degrees is the slope, you can see there's a potential problem here in that the gravity, the weight, this force is not parallel to the motion. And you should be picking up on the emphasis here that when we do these calculations, we have to use numbers that are parallel to the motion we're interested in. We've got some friction acting back up the plane here in this general case, but we'll start by doing a problem without friction. Well, let's simplify this to just the plane, a dot here for the person. The weight comes downward. We can still somewhat use the weight of the person, and weight is the mass times acceleration due to gravity, W equals mg. But this weight that goes downward here, we can find its components. We know how to do this. The weight is always the hypotenuse of the right triangle. One short side of this right triangle will be parallel to the plane. This is the one that will give us an acceleration, this component of the weight down the plane, W parallel. Then W perpendicular to the plane, that is going to be involved if there's friction present. For this starting problem, we'll have a normal force, a contact force with a slope with the skier, and that will be the same size as the weight. Those will cancel off. We won't have to consider those in this early chapter. But we're going to take advantage of our diagram here to help us find what the acceleration is down the plane. So let's suppose we put some numbers on this. The skier has 80 kilograms for the mass. Let's get rid of friction in this calculation. We'll bring friction in later in the course. What's the acceleration of the skier? Well, F equal ma is probably going to be used here. We have a mass. We want to know the acceleration. Well, it remains for under discussion, what is the force? This acceleration we want is directed down the plane. The force needs to be down the plane, the net external force that we come up with. Let's let up the plane be the positive direction. Now, this W perpendicular, for practice, let's go ahead and calculate it. It's adjacent to the angle theta, and this angle theta here is always the same as the angle of the ramp. And you can work this out. This is theta. Up at the corner here is 90 minus theta. We have another 90-degree angle between the plane and this perpendicular to the plane. So this would be theta. So W perpendicular, gravity is pulling the object into the plane with this effective force. 80 kilograms times 9.8 is W. That's the weight of the person. And then cosine of 25 gives us this force on this adjacent side to the angle. And I'm calling into the plane in negative direction, so I attach a minus sign here. I did that at the beginning. Minus 710.5 newtons. The component of the weight that's parallel to the plane, acting down the plane. Now we're opposite to the angle theta. So we need the sine function. And again, I just inserted the minus sign here because I can see from my diagram that this force is going down the plane. I'm choosing up the plane to be positive. So minus 80 times 9.8 times sine of 25 degrees, minus 331.3 newtons. In the direction perpendicular to the plane, the forces add to zero. Don't need to calculate any acceleration for that. Along the plane, without friction, there's only one force. That force is the component of the weight that acts down the plane, the side that's opposite to the theta. So minus 331.3 is our force. Putting this into F equal ma, we've got the net force. There's only one force, so that is the net force. M is 80 kilograms, and our A here, A value minus 4.14 meters per second. Minus 4.14 meters per second squared. Do you think this number is reasonable? Can someone going down the slope of a mountain that's at an angle of 25 degrees, can they actually have this number? It is reasonable. If they were free falling and off the edge of the cliff, that would be a parachute attached, of course. Before they pull the parachute cord, their acceleration would be minus 9.8 meters per second squared. So minus 4.14, that's reasonable. If they're on level ground, the acceleration would be zero, so moving horizontally. So we have a number here in between 0 and minus 9.8. That's reasonable. I'd like you to repeat this calculation on your own if the mass changes to 52 kilograms, and see if you get a surprising result or not surprising result. But you should repeat the calculation and ask questions in class. How about a person on a tightrope? As the person stands on the wire sags a little bit, and the free body diagram here shows the weight of the person going down. There are two tension forces. The wire is going to create a tension to the right, a tension to the left at the place where this person is standing. Let's suppose the person has a mass of 55 kilograms. What is the tension? Again, the free body diagram helps us with this. The tension has X and Y components. Each tension has an upward component. Tension to the left, tension to the right. There are Y components shown here. The tension has a component in the X direction, to the right and to the left. Those add to 0. Then we have the weight. So what does the tightrope person hope that happens? The hopes that the tension upward, these two components, add together and match the magnitude of the weight downward. The person wants no net force in the Y direction or the X direction unless they use the friction force and walk along the tightrope. We'll talk about friction later. But there are two tension forces upward, and they have the same size. So I'm just in my ethical MA here. I'm going to use two of them. 2 times the diagram over here. The tension is the hypotenuse. The upward component is opposite to the 5-degree angle, so we use the sine function. We have two of these, one on the left, one on the right. They're the same number, so I'm just multiplying 2 times 1 calculation and use T for tension. Instead of T right and T left, those numbers are the same. T right is the same as T left. So just use T for tension, sine of 5 degrees. Then downward, we have 55 kilograms times 9.8. mg is the weight of the person. And on the right side, the acceleration is 0. We want the person to not be accelerating upward or downward. The acceleration is 0. So you work this out, multiply this, these numbers to get the value here, add to get that off to the right side, divide by 2, divide by sine of 5 degrees. Hopefully you'll agree that 3090 is the value of the tension, over 3,000 newtons, a lot larger than the weight of the person. Roughly, if we take G to be 10 meters per second squared, the weight of the person is about 550 newtons. Again, kilograms times meters per second squared produces newtons for a unit. So the tension has to be a lot bigger. It's actually because this angle is small. Other places where you would see tension and a change in the shape of the object, chains, suspension bridges. You don't have a straight line here, you have a little arc, a little curve to it. This happens naturally as things are in a horizontal position. Another illustration of net force, and we won't do any calculation here on this video, but 2 tugboats pushing a barge, and they combine to produce an acceleration at a certain angle. There's some water resistance, some drag force that comes into play here, and you should set problems up such that you have components in the direction of motion. So we'd find the tugboat's force in the direction of motion here to do this problem. And then streetlights, again there's tension, and tension 1, tension 2. If the angle is different, then we can have some variation in the values of the tension. And we'll only focus in on forces that act on our object on the streetlight here. And we'll do some of these types of problems. So that's our little introduction to F equals MA, a couple example problems. You should read, ask questions, and work your own example problems.